And welcome everyone, and thank you for joining today's webinar. In this session, we'll explore how graph technology helps organizations solve some of their toughest identity and data quality challenges. Specifically, we'll look at how graph-powered entity resolution allows you to connect the dots, unifying fragmented data, uncovering hidden relationships, enhancing compliance, and delivering more personalized customer experiences. So my name is Sebastian Mansell. I'm Senior Director of Product Management here at Tiger Graph, and I lead our Savannah cloud product offering, which brings together the power of graph technology and the scalability of cloud to tackle complex data problems. Sam Zhou is our engineering lead for Savannah. Sam will walk us through a pre-recorded demo of how Savannah performs advanced entity resolution using graph capabilities built into the platform. So what is entity resolution? Entity resolution is the process of identifying and linking records that refers to the same real world entity, such as person, business, or product, even when those records exist across different systems, use different formats, or contain inconsistencies like typos, alternate spellings, or missing data. So why is this important? Well, entity resolution addresses three core data challenges. Duplicate records for the same individual or organization create noise. It creates conflicts. Data is often siloed in CRM systems, billing platforms, support databases, or contains partial information. And without resolving these fragments, you lose the full picture of the customer or entity. And real-world data is messy. It's hard to accurately match records when there are variations in formatting or errors in the data. Here is where entity resolution steps in. It matches and merges duplicates into a single trusted record. It links fragmented records across systems to provide a unified view of an entity. It handles inconsistencies through data standardization, probabilistic matching techniques, and increasingly AI and machine learning models that improve accuracy over time. Ultimately, entity resolution transforms messy, disconnected records into accurate, actionable views of real-world entities. So why does it really matter? Well, because every data-driven decision depends on trust in your data. Reports are skewed by duplicates, leading to flawed analytics. Customers receive irrelevant offers because their information is incomplete. And organization risks fine if they cannot meet regulatory standards like know your customers, anti-money laundering, or GDPR requirements. And fraudsters exploit these blind spots. Regardless of the industry, entity resolution is the invisible foundation behind trusted data, accurate decisions, and personalized experience. So let's take a look at the numbers, because the impact of entity resolution isn't theoretical, it's measurable, and it's significant across key business areas. So advertising and recommendations. When identities are resolved accurately, marketing becomes dramatically more efficient. According to McKinsey, companies see a 15% to 30% increase in marketing ROI when they personalize outreach based on unified data. And LiveRent reports that engagement rates rise by over 60% when personalization is driven by accurate entity resolution. That means more relevant offers, higher conversion, and better returns on your data investment. Fraud is one of the costliest threats to financial institutions and digital platforms. Experian found that fraud losses drop by 45% when entity resolution is used to verify identities and detect suspicious connections. And the digital ID verification market is booming. It's projected to reach $40 billion by 2027, according to Juniper. Salesforce data also shows that resolving customer identity across touchpoints can lead to a 25% improvement in customer retention. simply because you're engaging with the right person at the right time with the right message. And Accenture found that 80% of consumers are more likely to do business with a company that offers personalized experiences. None of that personalization is possible without resolving who the customer truly is across systems first. So whether your focus is on growth, compliance, fraud, or customer loyalty, entity resolution delivers bottom line results. Now, when resolving entities, how you match records defines whether your approach is deterministic, probabilistic, or machine learning based. Each method has strengths depending on your data quality and goals. Deterministic matching relies on exact matches using strong standardized identifiers like social security numbers or passport ID. This approach is ideal for clean, structured data where fields are consistent and complete. It is very effective at removing duplicates and reducing data fragmentation when PII fields are aligned. However, it struggles when fields are missing or inconsistent and minor data entry errors exist. So multiple identifiers don't align perfectly necessarily. And even strong identifiers like names and birth dates can be misleading. They're helpful, but they're not foolproof. Probabilistic matching is designed for messy or inconsistent data where typos, nicknames, or formatting differences are common. It uses fuzzy matching techniques to compare partial or similar values. So think of John Smith or Jonathan Smith or Jay Smith. It combines multiple weak signals, partial names, addresses, phone numbers, and calculates a matching score. So this method is especially useful when there are no strong identifiers available. Machine learning matching is the most flexible and scalable method, especially when dealing with complex relationships or non-obvious connections. But it does require example of true matches and non-matches. And so it needs training data to predict duplicates, even with minimal direct overlap, to identify weak but meaningful signals across multiple fields, or to generalize from prior patterns to fill in gaps or resolve uncertainty. All right, let's walk through how deterministic entity resolution works in practice. So we begin with multiple data sources. Here they're labeled source 1, source 2, and source 3 on the left-hand side. And each contains structured records like social security number, email addresses, phone number, gender, and so on. Now, these data sources come from relational databases and are mapped into a graph model. That's the first step. In the center, we see how these attributes become connected in the graph. So for instance, a shared social security number between two customer records allow us to infer a high confidence match. And that connection is then represented in the graph by an edge labeled customer_SSN. That edge links the two customer vertices based on this high confidence match. Now, once we've established this deterministic match, we merge these customer records into a single unified entity. That's what's shown on the right. This merge entity aggregates all attributes and edges from the original records. Now, what happens when the attributes conflict? So, for instance, if you have different addresses, age references, or even gender for the same customer record, well, that's where data governance and policies come in. And there's two common strategies here. One strategy is most recent wins. So for example, if the address from source 1 has a more recent timestamp, then the address from source 3, let's say, we choose the more recent one. And this is a common strategy when freshness is a priority, when you really need the latest and greatest data. Another strategy is store both as multi-value attributes. So if we want to retain all possible values for auditability or analysis, we can keep both addresses or names in the same attribute. And this helps in cases where we want to capture all the aliases or prior addresses, or even for gender transitions, for example. So the goal of deterministic resolution is precision. It's when we're confident that two records are the same based on a unique shared identifier, like Social Security, and then we merge them. And it's a great method when you have high quality data and a strong match key. All right, this diagram introduces probabilistic entity resolution. So each node here, A through G, represents a separate data record from different systems. Now, none of them have strong identifiers like Social Security number, for instance. So they appear disconnected. By evaluating similarities between their attribute values like name, email, phone numbers, and potentially their behavior as well, we start identifying relationships. And these weak signals allow us to form cluster based on their shared traits. So here we have similarity scores. We've added similarity scores to edges in the graph. So you see the picture changes dramatically, right? You're seeing the connection now, and you're also looking at similarity scores between each of these nodes. So these values like 0.95 or 0.89, they're computed using string distance or semantic similarity methods. So think about cosine or Jacquard similarity. And you might also add weights based on business rules or machine learning models. So there's multiple ways to get to these connections. When the similarity between two records exceed a certain threshold, let's say 0.9, we consider them potential matches. Scores in the 0.6 to 0.7 range may not be strong enough on their own, but they could influence matches in larger patterns. So some matches are nearly exact, others are inferred through strength of connection. All right, so now we have similarity scores, and we can form clusters of match records. So this is what you see here when with the values A through D and E through F now are part of a cluster. You can see that A through D share strong connections, and they're grouped into a unified field. That's where the Berry-Markin label comes in. And then records E, F, and G are similarly grouped as Barrel-Markin. So those two sound the same, but they're actually separate entities. And note that these clusters are formed using probabilistic logic, not exact field matches. So it's the structure and overall weight of similarity across multiple edges that creates these clusters. And this is really where a graph becomes powerful. It helps you see patterns, not just in field level similarities, but with all the connections that you can derive. So now let's walk through the machine learning pipeline for entity resolution. We'll look at this step by step. So on the far left, we begin with a graph representation of the data. So each circle marked A, B, C represents a record, and the red circles represent attributes such as email, phone, or address. Edges in this graph show records with shared attributes. And now this graph gives us context that traditional tabular data doesn't. Instead of comparing records in isolation, we can now see how they're connected through shared data points. Next is the feature engineering stage. So this is where we derive metrics from the graph to help the model make decisions. So we compute things like Similarity metrics between the records. Again, Jacquard or cosine similarity is a good example of that. We look at shared neighbors, how many attributes or entities they both link to. And then we look at path-based features. So this is really calculating how many hops apart are two records and whether they're part of a densely connected subgraph. All of this, again, we can get from this feature engineering stage. And next, we focus on those features. We feed these features into a model. So there's multiple models you can use. This is not a full list, but common ones are going to be XGBoost, which is a feature-based machine learning model that's fast and interpretable. And then you have graph neural network that works directly on the graph structure, learning relational patterns. Now, these models return a link prediction. So typically, a probability score indicating whether two records refer to the same real-world entity. And then finally, we use clustering to group the matched records. Here you see A and B were predicted as a match and are clustered as entity one, John Smith, while C was matched and retained on its own entity, J. Smith. All right, so let's look at a side-by-side comparison of the three main approaches to entity resolution, the three approaches we just went through. Deterministic methods are rule-based. They rely on exact matches, such as two records with the same social security number, or let's say the same passport number. They're fast, they're precise, and it makes them ideal for use cases that demand high precision and compliance. So think about government services. However, they're fragile. Minor differences or noise in the data can really break the match and make it less effective. Probabilistic approaches are more forgiving. They can account for typos, they can account for nicknames and variations in the data using similarity scoring and fuzzy logic. Now, these are useful for personalization and marketing, where you want to match users even if the data isn't a perfect fit. So the trade-off here is that they require threshold tuning and they can be trickier to calibrate. ML-based approaches offer the most flexibility and scalability. They can learn patterns from data, adapt over time, and capture relationships over other methods miss. And they're particularly valuable in high-stakes use cases like fraud detection. Now, the trade-off with machine learning-based approach is that they require labeled training data, and that's not always available. So the goal here is to align the method with the specific needs of your business problem. Many real-world implementation use a hybrid approach, combining deterministic rules with fuzzy matching, and then augmenting that with ML scoring when the stakes are high, like in fraud detection use cases, for example. All right, but matching entities is only the first step. To truly unlock value, whether it's for fraud detection, personalization, or compliance, you need to link those match records. Now, we'll walk through three common graph-based strategies for linking matched records after entity resolution. So the first one is matching link on the left diagram. This is the simplest model. When two records match, we create a direct edge between them. And you're forming a web of connections there. A graph of raw records is linked by shared identifier or similarity scores. Now, this model retains every record as a separate node. So it's great for auditability, and it's great if you need to track the data source because it retains all that information in the graph itself. Next is the unified entity vertex, the middle diagram. Here we introduce a new node, the blue vertex, representing the resolved entity. So once we've matched, all the entities, we link them to this. We create this unified node, and then we link all the matching entities to this node, and we create a hub that consolidates entity while preserving the underlying sources. Now, this approach is ideal for master data management and customer 360 use cases. It simplifies queries like, show me everything about this customer, even if the data comes from multiple systems and is distributed. Now, on the right-hand side, we have the merged entity. So in this model, we go even further. Instead of linking the records, we merge them into a single unified node. Now, all the data associated with the records, transactions, events, attributes, now point to this one entity, this one merged entity. Now, this gives you a clean and compact graph. It's optimized for performance and real-time analytics. And it's great for fraud detection or behavioral modeling, where the goal is a consolidated view and not a historical view of the data sources. But again, the trade-off here is that it reduces traceability because you've merged all the records into a single node, and the record provenance is lost. All right. So now that we've matched and linked the records, the next step is to derive business insight from the unified entity graph. And this is where the real value kicks in. So instead of siloed transactions and disconnected attributes, we now have a connected network that reflects a complete view of the entity. So let's look at what this enables. By understanding the unified profile, say all devices and accounts used by one person, you can deliver ads to the right person at the right time across all channels. So this is extremely valuable. This improves targeting precision. It minimizes, wasted spend. And it's very useful, especially when like cookies or user identifiers are noisy or unavailable. With entity resolution, all of the user's behaviors, searches, clicks, purchases is aggregated into a single profile. And then what that means is that your recommendation models operates on a much richer context and can be much more valuable. So this often leads to significantly higher conversion rates because the product recommendation is based on a complete view of the user's behavior. Now, Customer 360 is the classic use case for entity resolution. Once you've unified all the records related to a customer, your billing profiles, your service tickets, your chat history, transactions, and so on, you can build a 360-degree view of that individual. And this powers everything from personalized service to risk scoring, churn prediction, and much more. So in short, once you've linked the records, your graph becomes an engine for insights and a foundation for smarter business decisions. All right, so how do we actually group and activate all of these linked records? So this is where graph analytics comes into play, specifically with a technique called weakly connected components. Now, while it sounds very technical, the concept is simple. We're identifying all the records that are connected directly or indirectly, regardless of relationship direction. So in practice, this gives us clusters of records that represent a unified entity. Each cluster can include logins from different devices, for example, transactions from multiple systems, or even marketing activity across channels. And these clusters form the foundation for Customer 360, fraud detection, and personalized experiences. So while entity resolution links the data, the weakly connected component is how we operationalize it by surfacing the complete connected picture in a way that machines and analysts can immediately use. All right, so let's take a look at an example is in a marketing cloud setting. So step one, we start by merging the various device identifiers such as IFA, identifiers for advertisers, MSEC, typically secure mobile SDK identifiers, cookies and IP addresses into a single device UUID. So we essentially take all of your digital footprint and all the identifiers we can collect, and we use the graph to combine those into a single UUID. Now, these identifiers may originate from mobile apps, browsers, or backend systems, so they can actually come from different and disparate systems. But what we're doing in this step is really merging them together so that we have a complete view. Step two, we look at once we have the device level identities unified, we link these devices that share the same IP address or location. And what that does is it creates a household level vertex. And this allows us to cluster multiple devices or users into a single household entity. Now, next, we can generate personalized recommendation or apply segmentation to at the household level. So this is crucial for marketing teams targeting entire households rather than just individual devices. So let's look at the benefits. So in this example, which is a real world example, TigerGraph processed 1.7 terabytes of raw data using a batch graph algorithm, proving the platform's ability to handle massive data volumes at scale. And the system generated unified device and household identities with minute level performance, which was a major improvement over traditional ETL pipelines. Most importantly, we enabled real-time segmentation, meaning marketers can respond to user behavior or campaign triggers as they happen in real time. All right, we're going to now go through the Savannah demo. So I will go ahead and stop sharing my screen. And I will switch to the video.
Thanks, Sebastian. Hi, everyone. My name is Sam Zhou. I'm the engineering manager at TigerGraph. I'm super excited to introduce you to two fantastic solutions on TigerGraph Savannah that cater to different needs. First, the Entity Resolution KYC, which is Know Your Customers. It focuses on tackling financial crime, and the General Entity Resolution Kit, designed to help you create a comprehensive 360-degree view of your customers. You can create these entity resolution solution kits when setting up your workspace. Alternatively, you can easily add them to your existing workspace through the Marketplace Solutions menu here. For today's demo, I'll be using two pre-created workspaces. Let's start with the Entity Resolution KYC kit. This kit utilizes a standard financial crime graph schema. Similar to our other financial crime solutions, the core vertex here is the party. And our goal is to identify parties with similar P2 information. One of the standout features of this kit is its capability to handle incremental and online entity resolution. We can see that there are database, ID, card, email, full name that are linked to a party. We're trying to find similar parties with the same P2 data. We've included a variety of queries to demonstrate how organizations can maintain accurate and up-to-date customer information while combating financial crime. The key queries here is match party entities and unify party entities. To begin, we can explore the graph to check the current data. Let's check for the party, same as another party. We can see that there is no data yet. Now, let's run the match party entities query. You can adjust those parameters based on your need. Now, the query is done. You can see that we found 127 matched entities. Now, let's explore the graph to find parties, same as another party. And we can adjust the limit to 200 in this case. Now, we can see that those are matched entities we found using our query. To perform a unify operation, simply you can run the unify party entities query. Now, let's switch to the general entity resolution solution for connected customers. This kit features a unique graph schema tailored for achieving a complete 360-degree view of your customers. For this graph schema, we can see that we have more data compared to entity resolution KYC kit, including tax ID type, name hash, street address, and phone hash. Similar to the KYC kit, the key queries here are match entities and unify entities. Let's take a look at the match entities query. One of the standout features of this kit is its fuzzy matching feature that uses a mean hash approach. This allows you to identify similar entities even when the data isn't an exact match. Again, let's try to explore the graph before we run the query. So we're trying to find if there are any same as entities exist. There's no data. Now, let's run this query, match entities. Again, you can adjust those parameters based on your own needs. Cool. As one can see here, we found 487 matched entities. Let's go to Explore Graph. In this case, we want to find all of them. So let's make that into 500 to run it. There we go. We have all the matched entities showing here. Similarly, you can run the unify entities query to unify all of them. With that, let's conclude my demo today. Thank you, everyone. I'll give it back to Sebastian.
Thanks, Sam. So as you can see, this was a really great way to look at some of the logic that's built into Savannah, as well as some of the weights that you can assign. It's a very powerful capability. So I'm going to go ahead and go back to the presentation. Okay. All right, so let's take a step back and look at why graph databases are uniquely suited for entity resolution. First, they offer a natural way to represent complex relationships. Like, unlike tables, graphs connect the dots between fragmented, duplicated, or related data directly through edges. It really gives you the context alongside the content. Second, graphs enable multi-hop matching and pattern detection. So you're not limited to direct similarities only. You can follow chains of relationships, even subtle ones, to find hidden connections. And third, they're built for performance. It's real-time querying across massive connected data sets is what graph engines are really designed for, and they excel at it. And then finally, graphs support in-graph similarity scoring and ML integration. And, Sam showed some of those. So this means you can score potential matches, you can embed machine learning predictions, and you can update your resolution pipeline, all without moving the data out of the graph. So it's extremely, extremely powerful. So now let's talk about why customers choose TigerGraph for entity resolution. So TigerGraph was built for deep, multi-hop reasoning at scale. Our native parallel graph engine allows you to traverse 10 plus hops efficiently, enabling detection of patterns that span many, many degrees of separation. We operate at a massive scale with real-time performance. So thanks to distributed storage and compute, and dynamic partitioning, you can query connected data at speed, even in very large graphs. And our platform supports AI-enhanced entity resolution out of the box. You can integrate machine learning models via PyTorch. You can apply fuzzy logic and scores across graph patterns. You can build hybrid approaches using both deterministic and learned logic. And finally, TigerGraph gives you full control through a flexible query language. You can define your own rules, weights, thresholds, and fuzzy comparisons. You can even incrementally resolve records, updating only what's changed. So it's very flexible in that sense, and it makes the systems both powerful and efficient. So TigerGraph is a full platform for entity resolution at enterprise scale. We have the performance, flexibility, and intelligence to turn your data into